Hello, can you hear me okay?
Yep, I can hear you, Dr. Coogan.
Okay, great.
Yep,
Okay, there. It's letting me turn my video. Great. How are you?
I'm doing good. I'm doing good. How are you?
Good, good. You must be Nishant. Is that right?
Yes,
Okay,
yes,
great.
yeah, yeah. And Andreas, so just to give you a context, like this is gonna be streamed live on our YouTube channel,
Okay,
and all the participants, all the attendees will be on the live channel, and whatever questions they have, like I'll be relaying them to you at any point.
okay,
And
I see. So they're going to join
yeah,
via YouTube. Is that
yeah,
right?
yeah, yeah,
Okay,
yeah.
okay.
And how do you prefer? Like, do you prefer the questions at the end or as
No,
in?
they can
Okay.
interrupt with questions at any
Okay,
point.
okay,
That's
yep,
fine. No
okay,
problem.
yep. And
Um,
yeah, and my advisor, Dr. Malikopoulos, sends you its regards. He'll be joining the YouTube audience,
okay, great.
and yeah, he welcomes you.
Yeah, yeah, great. Um, will we start right at noon, or do you typically have a bit of a delay
Oh,
at
we
Cornell?
can start at noon, like
Okay,
at 12 is
great,
totally fine. Yeah,
great, great.
yeah. I'll just give an intro and then we can move on with the talk.
Okay,
And we can do we can start this at 12.
okay, great.
Yeah. Meanwhile, if you would like to uh, check if the screen sharing works and all of that, you could totally do that.
Sure, let's do
Yeah.
that. Um, let's see. Can you see that? Okay,
Yep, I can see it.
great. Good.
So I think there's like a 30-second delay to the YouTube stream. So
Okay,
yeah,
I
it's not
I see.
much of a delay.
I
Just a
see.
small. Yep. Dr. Coogan, I see that you've collaborated with Dr. Arsak. And,
Archak, yeah, he was my
yeah,
advisor. He was my PhD
okay, okay.
advisor at Berkeley. Yeah, that's
Yeah,
right.
he
I was
gave a
looking.
talk. Sorry, yes.
Yeah, I was gonna say I was looking at your seminar series. It's a very nice seminar series. You've had a lot of excellent speakers, including Marat, who was here a few weeks ago, maybe.
Yep, yep.
Yeah, very nice. Yeah. Do you do these every week, or what's the cadence of these?
Yeah, it's usually every week, and we keep it only during the semester, like the fall and the spring semesters.
Very
During
nice.
summer,
Yeah,
we just have a week. Yeah.
yeah, very nice.
We're trying to come up with more of a theme, and for this semester, it seems to be more on formal verification.
Mm.
I've seen Dr. Zamani, Majid
Mm.
Zamani, he gave a talk, and some point, Dr. Oche, Nime Oche,
Hmm.
she's
Hmm.
gonna give a talk.
Okay. Yeah, very nice. Yeah.
Yeah, yeah, we're trying to uh, bring in people based on some themes.
Right. Yeah.
Yeah, trying to build it up as we go along.
How long have you been doing the seminar series? Is it new this year?
Um, yeah, we started the fall, I mean, the recent fall, and it's our first year.
Yeah, very nice.
And yeah, we're trying to build the audience as we go on and invite like people from a bunch of disciplines, so it covers everything.
Yeah,
Yeah,
it's
yeah,
very nice.
yeah. I think we can get started now. Yeah, it's noon, so yeah. Yeah, hello everyone, welcome back to the DDLC seminar series, and this is Nishant, and today's talk is going to be about interval-based methods for efficient verification and synthesis of learning-enabled control systems. And the speaker for today is Professor Samuel Coogan, and he's the Demetrius T. Paris Junior Professor at Georgia Tech, and he's associated with the electrical and computer engineering as well as the civil and environmental engineering. His research interest is in the area of control theory and autonomy, and it focuses on developing scalable tools for verification, safety assurance, and control of robotic and cyber physical systems. And the emphasis is more on the transportation side. A biography about Dr. Coogan, and he received his BS degree at Georgia Tech, and he did his grad studies in Berkeley. In 2015, he worked as a postdoctoral research engineer at Census Networks, and in 2012, he spent some time at JPL NASA. And before joining Georgia Tech as an assistant professor, he was with UCLA from 2015 to 2017. And his awards and recognitions include the 2020 Donald P. Ekman Award from the American Automatic Control Council and a Young Investigator Award from the Air Force Office of Scientific Research in 2019, an NSF Career Award in 2018, and the Outstanding Paper Award for IEEE TCNS in 2017. And without further ado, I I'll let Dr. Coogan take on.
All right. Yeah. Thank you very much for that very kind introduction. It's a real honor and pleasure to be able to speak today during this seminar series. Feel free at any point to interrupt with questions as I go along. I understand that they'll be monitored on YouTube, and I'm happy to take them at any point in my talk. So today I'm going to talk about a class of methods we've been developing in my group, largely around interval-based methods where we leverage control theory and efficient computations for this problem of verification and synthesis. And so I'll motivate a few of the different versions of this problem we've been studying and tell you a little bit about some of the technical details that we've been using. So this picture is probably a picture you've seen or something similar to this in other talks in this seminar series. I think this is becoming a major research focus right now in the space of formal autonomy. And so the setting is the following. So we assume you have some nonlinear dynamical system, x dot equals f of x comma u comma w. So this is an ordinary differential equation that we would be familiar with. We might know something about its initial condition. U is an input that we get to control, and w perhaps is some disturbances that enter the system. But unlike the classic setting that we might be familiar with, the idea here is that we're closing the loop with learning-based controllers, depicted here as a neural network. We might also be coupling these systems with more complicated safety specifications or requirements as we go. And the goal is to somehow prove some verifiable property of the system. And in this talk, that verifiable property is largely going to hinge on our ability to compute what are known as reachable sets of the closed loop system. So this is the picture of a reachable set. You have an initial condition. You want to compute all possible states that the system could evolve to. And if you can verify, for example, that those states don't intersect an unsafe set, then you can declare, for example, that the system is safe. And I'll talk a little bit more about this in a few slides. The challenges here generally is that we might have high dimensional nonlinearities. They might already be present in the system, but even if they're not, we generally have high dimensional nonlinearities coming from the control strategy that we're using in this neural network. And in general, we then are posed, we have to kind of confront this efficiency versus conservatism trade-off. Methods that we develop, hopefully are both efficient and not very conservative, but this is generally not easy to do. And so we sort of have to trade off between these two. So in this talk, I'm going to focus on sort of a fast, interaction aware, and I'll explain what I mean by that, interval-based reachability framework for these types of systems. And it's largely going to be predicated on this, on control theoretic notions, and in particular, monotone systems theory, or a variant of that called mixed monotone systems theory. And so that's going to be a theoretical element to this problem that we're trying to address, shown in this picture. So before I dive into any of the details, let me just sort of give this motivating video of why this might be of interest. So this is a paper we published last year. This is what we have here is a human in this case, so not a neural network, a human, but we could swap it out, for example, for a neural network. The human is controlling what's supposed to be a hardware demonstration of a satellite, and so they're controlling it with a joystick. This is a hardware platform that's in a collaborator, Panasiotris's lab here at Georgia Tech. This is a spacecraft that's mounted on a hemispherical ball joint, a very low friction hemispherical ball joint. It's actuated by these air thrusters that rotates this aircraft, the spacecraft. And the challenge here is that it's got very low actuation capabilities. The amount of force that can be applied to the system is very low. And so to get the system to slow down and change direction takes quite a bit of time. So you might put a safety specification on this spacecraft. So for example, you don't want it to ever point in a certain direction. That's shown here in this experiment. There's a hula hoop on the wall. This hula hoop, for example, could represent the sun. There might be some sensitive instruments on the spacecraft. And as you reorient the spacecraft, you might be required not to ever orient the spacecraft in the direction of the sun. And so we mounted a green laser pointer on top of the spacecraft. And the safety specification, is pretty, in this case, it's pretty simple to state. You just don't want the spacecraft to ever point in the direction of the sun. But like I explained, it's quite difficult to anticipate where the spacecraft could go. If you have too much momentum and you're rotating, you may not have enough time to slow down before you violate the safety specification. So what we're doing in this experiment is we're constantly computing reachable sets of the system. We're constantly computing where the system could go to over the next 10, 20 seconds, even subject to disturbances. And we're making sure that under the worst case scenario of the disturbances, the best case scenario of what we can do, we want to make sure that we can avoid this unsafe set. And if we ever get too close and we get too close to this edge of safety, we have to pull back and override the human's joystick inputs. And again, the idea here is this needs to happen well in advance of us actually violating that safety constraint, because we need to have enough anticipatory capability to slow down before we do that. So this is sort of just the high level motivation for why we're interested in these, these reachability problems. And again, this is a complicated problem. This is a high dimensional system with some interesting nonlinearities that evolves on an interesting manifold. And so there's lots of things we have to do under the hood to make this work. All right, so many of you might be familiar with this idea of what a reachable set is for a dynamical system, but let me just try to step through it a little bit. So in this case, we have a dynamical system, x dot equals f of x comma w. Right now, I'm not writing it with a control input, just a disturbance input. Again, this could be because, for example, we've closed the loop with a neural network controller. We have some unknown disturbance. And the reachable set of this system, it characterizes all possible system evolution of the system. So for example, we have an initial condition x1, and we evolve the system over some horizon capital T. We might end up here at the state x1 of capital T. There's disturbances in the system. So even if I were to initialize in exactly the same place, I could end up somewhere slightly different. Of course, if I initialize somewhere else, I will generally end up somewhere else. And if I have a set of initial states, shown here as this orange square, I could try to sample all of these different initial conditions, and I'll get some sort of sampling of the output. And then if I were to sort of draw the exact correct envelope of all of these samples, this would be what we might call our time t reachable set, right? And so as I sort of motivated on the previous slide, having access to this set is very helpful. It's a very important kind of component in many different control applications, especially around verification and safety. In general, it's very difficult to get a hold of the true reachable set of a nonlinear dynamical system. And so what most of the work in the literature does, and what we will do also, is compute over-approximations of these reachable sets. And so we might be interested in sort of over-approximating it with different set representations. Here I'm showing an ellipsoid. And the reason over-approximations are generally the preferred type of approximation is because we can still do correct and sound safety checks. And even some liveness checks with these types of over-approximations. So for example, if I have a region of the state space that I know to be unsafe, with an over-approximation, if I make sure that over-approximation doesn't intersect the unsafe set, that's a sufficient condition for the real reachable set not intersecting the unsafe set. Likewise, if I have a target set that I'm trying to reach, if I make sure that the over-approximated reachable set enters and eventually reaches that target, that's a sufficient condition for making sure that the system will indeed reach that target. So in general, over-approximations, not always, but in general, over-approximations are the right set representation for a lot of the verification and synthesis analysis we want to do. Okay, so again, I told you that the challenge is computing reachable sets of these systems. We generally want to resort to over-approximations. Let me tell you about a particular class of systems where the exact a kind of reachable set over-approximation can be computed very efficiently. And in a certain sense, it's the tightest over-approximation. So let me motivate that with this idea of a monotone dynamical system. So a monotone dynamical system is a certain class of dynamical system that has the certain following property on sort of monotone ordering of its states. So this blue box here says if I have a set of initial conditions, x naught, it's a vector, and I have another set of initial conditions, x naught prime, it's another vector, right? And they're ordered in general with respect to some partial order, but for concreteness, we can think of this as with respect to the usual partial order. So that means that every entry of the primed initial condition is larger than or equal to the entry of the non-primed initial condition. We would call the system monotone if that ordering relationship remains true as the system evolves over time, right? And that's depicted down here. I have an x prime. It's larger than some other state x. And as the system evolves, it stays ordered with respect. The ordering remains as the system evolves, right? And then if I have disturbances, I would want this to be true, perhaps for every ordered disturbance as well, right? And so that's the condition for monotonicity. It's kind of a strong condition, although there are many interesting real-world systems that exhibit this property. And the nice thing about this property is that there's a very simple test based on partial derivatives of the vector field that you can do to test if your system is monotone. So in particular, what you do is you check all of the entries of this Jacobian matrix, partial f of partial x. This is in general a square matrix. Its dimensions are equal to n by n if your system is n-dimensional. And you want something like positivity in all of the entries, but you actually don't care about the diagonal entries. So what you want to actually is that this matrix is Metzler. That means its off-diagonal entries are non-negative. And again, this diagonal piece, the irrelevance of the diagonal comes from the fact that we're working in continuous time. It's just an artifact of sort of how that math works out. And then you need a similar type condition for the partial derivatives with respect to the disturbance inputs. But now I want, this is in general a rectangular matrix, and I want every entry to be non-negative. So this is a well-known class of dynamical systems. It's been, well studied and really codified in this 2003 paper by David Angeli and Eduardo Sontag. And so this is a well-known class of dynamical systems. Why is this class relevant for reachability analysis? Well, it's very easy to compute an over-approximating set for the reachable set. So in particular, what I need to do is I just compute two real trajectories of my system. If I have a box of initial conditions, that's shown here with this pink rectangle, I take the lower initial condition, this x underscore, this larger initial condition, this x overscore. I evolve those two trajectories of the system. Those are two real trajectories of the system. And then I draw a box from the endpoint. That box contains the true reachable set of the system. And this is the property of monotonicity manifesting itself in this reachable set computation. So that's what this picture shows. And it also has this kind of interesting property that this is the tightest box that contains the real reachable set. There is no tighter box that would contain the real reachable set. Of course, it's still an over-approximation. The real reachable set might have some interesting nonlinear shape to it. But this is the tightest over-approximating box for the reachable set. All right, so certainly not surprisingly, if my system is not monotone, I generally don't have this nice property where I just need to compute two trajectories of the system. So here's a very concrete example where I see that the real reachable set of the system sort of extends beyond the rectangle I would draw from these two trajectories. So this tells us that, this is it's a very interesting property, but it is restricted to monotone systems. So what we've been focusing on in my research group for a number of years now is how can we exploit this monotone systems property even on systems that aren't monotone? And it seems like a really good way to do that is to take our non-monotone system and embed it in a particular monotone dynamical system. And we can do that using the theory of mixed monotonicity. And so this slide is a very quick summary of this very rich property and very rich extension of monotone systems theory. So if I give you, again, this dynamical system x don equals f of x comma w, and I have a disturbance input. And for the sake of simplicity, I'm going to assume my disturbance itself also lives in a box with w underscore and w overscore. Here's the mixed monotone approach to reachability analysis. What you do is you have to find something called a decomposition function. And you can kind of think of it as two different functions, a d underscore and a d overscore. These decomposition functions take in twice as many arguments as the vector field. So if the vector field takes x and w as its arguments, the decomposition functions take in two copies of something with the same dimension as x and two copies of something with the same dimension as w. And it has this interesting ordering property where if I substitute in the same arguments, x and x, and I repeat it in the first two arguments and w in the second two arguments, I have this sort of ordering relationship between the vector field and the decomposition function. And so what this tells you is that the decomposition function somehow sandwiches the vector field of your original system. And ideally, you want to try to get equality on in this first requirement, which you can do sometimes. Then the second important property of this mixed monotone decomposition function is you need it to be the case that when I construct this higher dimensional system, which we will call the embedding system, you want this system to be monotone. And there's a slight caveat here. You want it to be monotone with something called the southeast partial order. The southeast partial order is defined on R2n, and it's defined in this, it might be a little bit mysterious at first, but it's actually not a difficult partial order to understand. If I take a pair x and x hat, and I take another pair y and y hat, I say that the pair x hat is less than or equal to the pair y hat if x and y are ordered in the usual way, but the hatted variables are ordered in the opposite way. And it's called the southeast order because if I did this in two dimensions, if n was equal to 1, then the positive cone would be the southeast cone in R2. So that's why it's called the southeast ordering. But this is the requirement. So on the decomposition function. So if I have a decomposition function, what this essentially allows me to do is it allows me to sort of take my original dynamics. They're now sandwiched with these decomposition functions, and these decomposition functions define a higher order monotone system. And in a minute, I'll tell you about how to compute these decomposition functions. Let me tell you what you can do if you happen to succeed in finding these decomposition functions. What you get to do is you get to compute over-approximating reachable sets essentially as efficiently as if the system was monotone. And what you do now is you compute a single trajectory of this higher dimensional mixed monotone embedding system, right? So instead of two trajectories of an n-dimensional system. I'm computing one trajectory of a 2n-dimensional system. And then I take that trajectory and I sort of just break it apart into its first n components and its second n components, and then it gives me an over-approximating reachable set for my dynamical system, right? So this system's evolving in R2n, but it's almost like it's evolving in sort of this interval space where I'm tracking these lower and upper corners of a rectangle. And so this is now the picture for the same system I showed a few slides ago. If I do this operation where I find these decomposition functions and embed it in a higher dimensional space, I can compute these reachable sets as shown here, and I will get this over-approximating rectangle for the dynamical system. So on the left, I'm showing this in sort of the reachable set space, thinking of rectangles evolving to rectangles. In the next two plots, I'm showing this in projected embedding space. So this embedding system now has 4 state dimensions. I, of course, can't plot them all at once, so I'm plotting the x1 versus x1 hat, and I'm plotting x2 versus x2 hat. I guess I drew it with these under bars and over bars, but I'm projecting to the sort of the pair of x1 variables and the pair of x2 variables. And in that embedding space, I'm evolving the system from sort of this lower corner to this upper corner, and from this lower corner to this upper corner. Okay, you can do more than just compute reachable sets using the monotone embedding system. Because we're thinking this is a dynamical system, we can now think about stability in this higher dimensional space. And there's this really interesting connection between stability in this higher dimensional space and forward invariance in the space of rectangular reachable sets. So in a paper from a few years ago, we showed that if you can find some point in this higher dimensional space where the vector field points in a certain direction, so it's got this non-negativity with respect to the southeast order. So for example, a special case would be if you happen to find an equilibrium point where this is actually equal to 0, then you have this very interesting property. The rectangle that corresponds to the trajectory initialized at this point is robustly forward invariant for every point in time in the future, including at time 0. These reachable sets sort of nest as you go along, and the limit exists. So what I do, if I were to evolve this embedding system, it would shrink to some rectangle, and that rectangle would be some sort of smallest, the approximation of the smallest forward invariant attractive set for the initial box x naught, x naught. And so what this lets us do is, for example, is we can compute these forward invariant reachable boxes for these systems by thinking about looking at equilibria and directions of the vector field in this embedding space. And so there's this really clean connection between reachable set theory and stability theory of the embedding system. And this is something we'll exploit later in this talk as well. So to sort of summarize, and again, this is a problem we've been working on for a number of years now, this mixed monotone approach is extremely fast. A single trajectory of this embedding system bounds the reachable set of the original system. And we sort of have swapped out sort of this uncertain disturbance set. We've looked at its extreme corners, and now that lets us think about a deterministic embedding system as well. So I don't really have to think about propagating disturbance sets either. It's just a single trajectory of an ordinary differential equation. I can literally go call ODE 45 or some other, my favorite ODE solver, and get these trajectories. It's also very scalable mixed monotonicity. It scales to high dimensional systems. For example, if I find an asymptotically stable equilibrium in the embedding space, this gives me an attractive and robustly forward invariant set for the system, regardless of the state space dimension. I guess the downside of mixed monotone systems theory is it's got this over-approximation flavor to it. I'm computing over-approximations of the reachable set. So while all of these results are sound and sufficient, they could be conservative. And really, to be honest here, the conservatism is a big piece of the challenge of monotone systems theory, and it's where we've been focusing a lot of our effort, especially in the past, I would say, 18 to 24 months, is tackling this conservatism. So here's some recent research objectives that we've been focusing on in this space, and I won't be able to talk about all of them today, but I will sort of be able to address them bit by bit. So the first is, totally automating this decomposition computation. And we've been using the theory and the tools of interval analysis. Early on in our exploration, we really thought about this very analytically, and we wrote down decomposition functions very analytically. In the past, again, year or so, we've really totally automated this, and we can use interval analysis theory to automate, in fact, automate computations of entire families of decomposition functions. We've really been focusing a lot on this computing reachable sets of these neural controlled feedback systems, like I motivated on the first slide. And then sort of coupled to that, using this theory of robustly forward invariant sets, we've been focusing on training forward invariant sets for these neural controlled feedback systems. There's an interesting connection to control contraction metrics. And so if you're familiar with the work of control contraction metrics, I'll very briefly mention some very new and interesting work on that connection. And then I'll talk a little bit about extending this to complicated specifications beyond sort of reachability, obstacle avoidance. We spent a lot of time in my group thinking about temporal logics in particular, and that's a whole different sort of intellectual field to kind of think about. And so I won't go into too much detail there, but I will talk a little bit about our work thinking about signal temporal logic specifications. And then we've also had some interesting work extending this to reachability on manifolds that I'll very briefly highlight as well. So let me talk a little bit about the computation side, thinking about these automated decomposition functions. So let me just very briefly tell you what an inclusion function is. If I have a function g that in general maps from Rn to some other dimension Rm, an inclusion function for g, we write it as this pair, capital G underscore and capital G overscore. And what it does is, if I sort of give you this box, it over-approximates the function evaluation on that box. That's how you think of this inclusion function. Mathematically, what that means is, if I were to evaluate g underscore at x and x hat, these are sort of the corners of the box, it lower bounds the real function evaluation for any point z contained in that box, x, x hat. And this g overscore upper bounds that, okay? So I guess this picture sort of shows that this is some particular nonlinear function that maps from two variables to two variables. It's nonlinear, so if I were to sort of sample a box of initial conditions, it might output this red scatter plot. And an inclusion function basically over-approximates this with some sort of box. And you can get different kinds of inclusion functions. So here I'm showing you two, a blue one and a green one, and it doesn't really matter how I get these. But the point is there might be different kinds of inclusion functions. So of course, this is not new theory, understanding how to compute inclusion functions, and there are natural ways to do this. If I write down an equation and I can sort of decompose it into its constituent functions and constituent operators, and I can extend all of this to intervals and get certain kinds of inclusion functions. So this is not new. Surprisingly, perhaps for us, there did not exist a good toolbox for doing this in Python. And so we've actually developed two different toolboxes. We have one that we call NP interval. What this does is it extends NumPy, and it makes a native data type that is intervals. And so we can do very fast and efficient interval computations with NumPy. In the NumPy framework, using NumPy syntax, it's all very efficient and very fast because we've actually implemented intervals as a native data type. And so I'll talk a little bit about how we've been using this in our signal temporal logic work. A little bit more recently, we've also written an interval arithmetic toolbox, and actually quite a bit more in this toolbox that we call IMMRAX, which is an interval analysis toolbox written for JAX. So if you're familiar with JAX, it's this framework, it's this Python-based framework for implementing different, for extending to other kinds of frameworks that inherits things like auto differentiability, just-in-time compilation, parallelizability. And so we've done that for interval analysis. And this is really what lets us do analysis on, for example, neural network systems. And so I'll talk a little bit about that as well. But the point is that if I can compute an inclusion function, then I can essentially immediately compute this decomposition function. So that's the connection between interval analysis to mixed monotone systems theory, is if I can find inclusion functions, I can find decomposition functions, right? And it's not too hard. The decomposition function is almost exactly equal to the inclusion function, but there's this slight caveat where since I'm in continuous time and I'm trying to compute reachable sets, I need to do this sort of trick where I want to evaluate the inclusion function on lower dimensional faces of a hyperrectangle. So the details are a little bit messy, perhaps, but instead of getting an inclusion function that gives me a full dimensional hyperrectangle for my system, I really care about how it affects different components because I'm going to evolve a continuous time system. So I have to do this inclusion function evaluation on different faces of this hyperrectangle. And that's what this notation is trying to do here. And then this bottom plot just shows me that for different kinds of decomposition functions, I can get different kinds of reachable sets. So, on the left, this is perhaps a bad decomposition function from an accuracy perspective, but it is a pretty fast decomposition function to evaluate. And so there's this bit of a trade-off here. And then as we go to the right, we get sort of more accurate decomposition functions, but it might come at the expense of computation. So this is kind of the game you play a little bit in this monotone systems framework. Okay, so now let me talk about this first problem, this reachability of neural controlled systems, a problem that I brought up on slide 1. And so just to kind of recap the setting, I have a dynamical system, and now I might superscript it with OL for open looped. This is a dynamical system, and it has a control input U, and it has a disturbance input W. And I'm going to close the loop with some neural network controller. And in the next few slides, I'm going to assume this is given to me. Somebody else has trained a neural network controller, and our job is to make sure that that neural network controller does what it's supposed to do from a safety perspective, for example, from an obstacle avoidance perspective, right? And so what I can do, of course, is I can write down the closed loop system where I substitute in the neural network for the control input. And now I have this closed loop dynamical system, but it has this high dimensional nonlinear neural network embedded into it. And so what our goal will be is to compute reachable sets of this closed loop system. And we're going to do that in the following way. We're going to first use an open loop decomposition function for our original system. So we'll use our usual tools to compute this decomposition function from an inclusion function. And then what we're going to do is we're going to get our hands on an inclusion function for the open loop controller. And for this, we're going to use existing results from the machine learning community, where they have quite a growing suite of tools for over-approximating the image of a neural network. If I give you sort of a set of inputs to a neural network, there's a growing number of tools that overestimates the output set of that neural network. And we're going to use a sort of a particular type of over-approximation in the next few slides. And then what we're going to do is, once I have these open loop decomposition functions in this inclusion function, I will construct a particularly careful embedding system. And then I'm just going to evolve that embedding system like I described to get an over-approximation of the set. And then sort of this extra thing you can do that I'm not going to talk about in this talk, but that we did talk about in a CDC paper recently, is I can do some very clever partitioning as well, based on how fast these reachable sets are growing. That's based on this contraction metric. And I can try to be very careful with how I partition the state space in both time and in space, which I think is an interesting problem. Okay. So let me show you the results for this and how this works. Again, the challenge here is blending this decomposition function for the open loop system, which I told you how to compute, and these inclusion function for these neural networks. So for example, we're using alpha beta crown. I guess I cut a couple of the slides on this because they were a little technical, but we can find them if there's questions about this. But what we're basically doing is we're finding these affine under and over approximations, these local affine under and over approximations of the neural network. We're using known tools for that in alpha beta crown, but we're being very careful about where we're evaluating these affine over and under approximations, and we're being very careful to incorporate these affine approximations into the decomposition function in the open loop dynamics so that I don't accidentally compound the conservatism too much. I really want to make sure that if there are stabilizing effects in the controller, I'm accounting for them in this closed loop embedding system. So here's a demonstration of how this works. So this is a dynamical system. It's got 4 states. It's a kinematic bicycle model. It's got position in the XY plane, PX, PY. It's got a velocity V, and then it's got this heading angle phi as well. And you can see that, and then there's a steering angle, that's the input. The input goes through a steering angle. And you can see that there's pretty complicated nonlinearities here. There's cosine, sines, this sort of arctan function enters in a pretty nonlinear way. And then there's 2 inputs. There's this steering wheel angle, that's U2. And then there's the acceleration, U1. So, and what we've done is we've trained a neural network to drive this system from some sort of set of actually we trained it for the whole state space, and we're trying to drive it to the origin 0, 0 while avoiding this obstacle region here, right? And so what we did is we just sort of did a bunch of open loop optimal control solutions to this, and then try to train a neural network based on these open loop optimal control solutions in order to get this neural network controller. And so what we're showing here on this plot is reachable sets of the system computed over time. These reachable sets, we're trying to verify this safety property, right? So if I initialize, in this particular region up here, can I verify that this neural network controller avoids this obstacle region? And what I'm showing in these different plots are, the titles are, you have to read the paper to sort of understand the titles. But the point is that there's sort of different ways you can exploit this mixed monotone property, and you can and there's this trade-off, as I've been explaining, between conservatism and efficiency. And there's also some naive approaches to this problem. So this upper left corner would be sort of a very naive approach to this problem, where you just view the neural network as some disturbance some black box that's creating disturbances to the system. This would be a very bad idea. It doesn't capture any of the coupling in the control structure. And as expected, when you make that very coarse analysis, it's got a pretty fast computation time, but your reachable sets are very, very bad, right? But what we're showing in this kind of sequence of plots is we can get, with more and more clever decomposition function construction and incorporating these affine approximations of the dynamics, we can get all the way down to this lower right corner where we're getting much better reachable set approximations of the dynamics. And really the computation cost is very low, right? It's not even 2x the time it took in this very naive setting. And so this is really the power of this mixed monotone systems theory is this computational efficiency. That was a 4-dimensional system. I think it's very interesting to think about how this would extend to higher dimensional systems. So we made our own little benchmark here for this. This is kind of the same problem. We have a vehicle driving around an obstacle, but instead of just being one vehicle, now it's a platoon of vehicles. The first vehicle is controlled by a neural network. The rest of the vehicles are using proportional derivative tracking. And what we're trying to do is we're trying to verify that the rest of this platoon also doesn't intersect the obstacle, for example, right? And what's kind of interesting here is I can kind of scale the size of the platoon that I'm driving the system with. So that's what we see here in this table. This is the number of vehicles I have in my platoon, 1 up to 50. Of course, every vehicle introduces 4 state dimensions, so that the dimensionality of the state space ranges between 4 and 200. And then we have a neural network, of course, that has several hundred neurons that adds its own kind of dimensionality to the problem as well. And what we see in this plot is we're comparing 2 different versions of our method. There's an interconnected and an interaction method. In general, the interaction method is higher accuracy. So that's the top and the bottom plot over here. The interaction method is the one on the bottom. So it's got higher accuracy, tends to be a little bit more computationally expensive, but it still is dramatically more efficient than sort of the best other methods we know of. There's a method called Polar and a method called Julia-Reach. And they can do this problem for these lower dimensional states, but then and actually Polar can do them all the way up to 50 states, but you can see it's almost 2 orders of magnitude slower than even our more accurate interaction method here, right? And Julia-Reach just fails to compute as you go to higher state dimensions. So this is really where our method shines is these high dimensional systems. We really do not pay too much of a price because we're using this monotone systems theory framework. Okay, so let me tell you about another problem we've been interested in. It's very similar, but the setting's a little bit different now. So now the setting, again, we're still controlling a dynamical system with a feedback policy. And unfortunately, I changed the notation on you. So I was using n, but now I'm using pi for my neural network controller. Sorry about that. But I'm going to try to compute this neural network control policy. But now I want to train. So instead of just having somebody hand me the neural network and me verify a property of the system, I want to try to train that neural network to achieve a certain property. And what we're going to do here in these few slides is we're going to try to train this neural network to render a forward invariant set for the system. And so you can imagine why that makes sense, right? I'm trying to control something and I want to get some sort of stabilizing controller and I want some verifiable region where I know that stabilizing controller is valid and will keep the system over time, right? What we're going to do is we're going to look for polytope forward invariant sets. So a few slides ago, I told you we can use these tools to find hyperrectangular or box forward invariant sets. Turns out box forward invariant sets is pretty restrictive in general, right? That this picture is sort of showing that. Sometimes there's many systems where no matter what box I draw, I just can't get that box to be forward invariant. So what we've done here is we've extended these this theory to more general polytopes. There's some very interesting theory under the hood here. What we have to do is we have to take our system before we embed it. We have to lift it. Just to get a different word. So we now lift this to a higher dimensional system, and then we embed it in a system that has twice as many states as that lifted system. So you can imagine we're adding a lot of states to the system, but and so there's that aspect to it. But the advantage is we get very efficient computations even in these high dimensions. And so what we do is we use sort of the shape matrix of our polytope. That's this H matrix. If our polytope is written in half space representation, this gives me a matrix H, and I use this H to lift the dynamics, right? So it's a tall matrix because I'm trying to create a polytope, so the half space representation is a tall matrix. So for example, maybe my polytope is dictated by m half spaces, and so what I'll do is I'll take my n-dimensional system, I'll embed it in this m-dimensional system. And it's not difficult, or how we're doing that. We're basically just sort of rewriting the state variables in terms of this tall matrix. And then what I'm going to do is I'm going to apply the mixed monotone theory, but I'm going to do it to this lifted system. And what that lets me do is it lets me find forward invariant polytopes for the original system instead of just forward invariant rectangles. And that turns out to be very important. And the other takeaway here is that the theory is very interesting, but it is sort of messy and complicated. But all of this is abstracted away in this toolbox that we've been developing IMMRAX. So the user can just come in and define what polytope they're looking for, and then and attempt to solve and train a neural network controller for this polytope. So here's a benchmark we took from the literature. I think the citation shows up later, but this is I think it's a 4-dimensional segue because we have phi double dot here. So it's a 4-dimensional model of a segue, right? So it's a sort of kind of like an inverted pendulum, basically, that moves. And we're trying to find a stabilizing controller with a guaranteed forward invariant region for the system, right? So here are the state variables over here: velocity, tilt angle of the segue, and applied voltage at the motors. This is a problem that was posed in the literature a couple years ago, this problem of finding a forward invariant neural network controlled set. And we applied our method to it. So the caveat is our method, we found a forward invariant polytope. Our forward invariant polytope happened to be sort of flat in one dimension. That had the artifact of reducing the volume by quite a bit. So this other method was able to find a larger volume polytope. We think if we kind of continued to tweak that, maybe we could have fixed it. But anyway, in this particular example, we have a much smaller volume, but the time it took to prove stability of this controller and find this verified forward invariant region was significantly less than these other methods, right? And there's several reasons for that. These other methods, you have to sample on the exterior of the forward invariant set, and it's just very expensive and complicated to prove forward invariance. Our method, again, because we're embedding in this dynamical system, because forward invariance amounts to essentially stability of an equilibrium point in that embedding system, it's very efficient for us to include that in the training process and also verify it during training. So that's what we see in this plot. And that's just the polytope showing from several initial conditions we do indeed converge to the origin for our system. Here's another case study. Again, it's very similar to our platooning example I described a few slides ago. We tweaked it a little bit so that our forward invariant sets didn't grow as the platoon size increased. So there's some kind of increased connections between the vehicles. But the point is that our method, we can go from, in this case, I guess we went from 4 vehicles to 28 vehicles. So we had our state space. We also changed the dynamics a little bit, I guess. These weren't bicycles. These were sort of double integrator vehicles with some saturation on the control input. So our state space went from 8 to 56 in this example. There's this lifting operation, and so that increases the state space a little bit. But the point is that our training method is able to work here, and we can train polytopes for these pretty high dimensional systems, right? This is a 56 dimensional system or an 84 dimensional system, depending on how you think about it. And we can do this pretty quickly, just on the order of minutes, using this IMMRAX toolbox. And this just shows you the polytopes we're finding for the system projected to an individual, to 4 different vehicles. Okay, so that's sort of our work on neural network controlled systems. We've been using a lot of these same tools in theory for more complicated safety specifications. So you can think of neural networks as bringing a layer of complication to the control strategy. Another angle that we're very interested in is bringing a layer of complication to the safety requirements, right? And possibly bringing both, right? So I'm not going to give you a talk on single temporal logic. If you've seen these, you can do half a talk just trying to summarize what single temporal logic even is. I think for the purposes of this talk, it's sufficient just to understand that single temporal logic lets you formally specify things that are more complicated than just avoid that obstacle or reach that goal region. So for example, you might have some sort of hazard region and you want your state trajectory to avoid it, but it's kind of a soft avoidance. You want it to avoid it for at least n consecutive time units in any rolling window of W time units, right? So, maybe it's a temperature source and you can withstand high temperatures, but only for a limited amount of time, and it takes a certain amount of time to cool off, something like that, right? And the point is that, I could just try to avoid this region, but that might be too much. So I might want to let my system evolve into that hazard region, but I wanted to satisfy this requirement, this N and W requirement, right? So the point is first of all, I can write this down formally using, this temporal logic syntax, right? And I won't go through the syntax in too much detail, but the point is that this syntax is built from these predicate functions. So we can think of, predicate functions as sort of being whatever's defining the obstacles and goals in your state space, right? There's these temporal operators, which is sort of its own hieroglyphic kind of thing right here, right? We have diamonds, which mean eventually, and boxes, which mean always. And then we can also kind of connect them with Boolean operators, right? And this is regular signal temporal logic. What we've done in this paper and a couple papers is that we've been extending this to deal with intervals so that we can then couple them with our reachable set computations, right? And so let me try to briefly explain what we've been doing with this, what we call interval signal temporal logic. So it's both we're proposing kind of extension of signal temporal logic, and then we're also proposing the correct computational framework for dealing with this extension. So just at the definition level, this extension simply allows us to have interval valued signals, right? So instead of saying, here's the trajectory of your system over time, we can say, here's the intervals that your system was in over time, right? And we can also have interval valued predicates. So maybe instead of saying, here's the exact location of the obstacle, we can say, here's sort of a set where your obstacle is defined by maybe intervals on parameters of some function or something like that. And then with this definition, we can define what's called an interval robustness metric. This tells us if we satisfy our specification and by how much we satisfy their specification. And it's now given as an interval because depending on exactly which, where we sample from this interval, we'll get different robustness values. So now we have this interval robustness semantics. And the other really important feature of this is because we're leveraging this idea of interval arithmetic inclusion functions, because we're leveraging our computational tools that we developed with NP interval and with IMMRAX, we can do the verification and synthesis algorithms, right? So there are known verification and synthesis approaches for regular signal temporal logic, and we can apply them using our interval extension with essentially minimal changes, both from the coding level and from the computation level. So literally, if you wrote your code using some of these known STL pi toolboxes, if you just imported our interval extension of NumPy, and then imported our slight modification of these signal temporal logic toolboxes, you can, with very minimal changes to your code, you're suddenly working with uncertain systems, with intervals, with uncertain obstacles as well. And because we have intervals, essentially the computation time doubles because we have to deal with lower and upper extremes of everything, but that's not too much of a price to pay. No matter what computation time you were kind of willing to pay, initially, in this uncertain setting, you're paying roughly 2x times. There's a little bit of extra computation time for the overhead involved, but it's roughly twice as expensive. So here's an example of how you could use this, right? So it's a double integrator system. So we have an output y. Your input is the second derivative of y. There's some disturbance as well, so you don't know exactly what acceleration you're applying to the system. We discretize the system over some delta t. And your specification is as follows. So just to give an example of the kind of specification you can encode with signal temporal logic, the specification is there's this good band, this middle band where you would like to be. You're allowed to exit the middle band, but you can only do so for sort of 2 units of time, and then you have to go back to that region, and you have to be within that region for 2 units of time on any rolling window of 4 units, right? So I can leave, but I have to come back regularly, and I have to spend a certain amount of time back in this region of safety, right? So in this plot, we have uncertainty in the dynamics. We also have uncertainty in this region, right? So, and that's represented here with these red bands, right? So mathematically, we have intervals on some affine functions. Pictorially, and there's bands where we don't know exactly where this region is. And so what this means is, like, for example, when I'm trying to figure out if I'm in the safe band, I need to have a conservative estimate of that. So I sort of need this inner approximation. And when I'm asking myself, am I outside of the safe band, I want my I want this conservative approximation on the outside of the band. And so the point here is this specification, it's mixing and matching what it means to be inside, what it means to be outside. So to have a conservative approximation, I might have to sometimes be thinking about the inner approximation of this safe set. Sometimes I have to be thinking about the outer approximation of the safe set. And to do all this by hand, first of all, would be very error prone, and B, would lead to lots of different things you're checking. But if I just use the theory of interval signal temporal logic, and I think about all of this in as intervals being computed with inclusion functions, it just all happens and falls out very naturally and easily. And I don't have to think about it as the user, and the code takes care of it under the hood. So that's what, and so you get sort of this kind of plots here. If I were to solve this as a receding horizon optimal control problem, I might get this sort of control signal that you see here in blue, or sorry, not control signal. You might get this sort of output signal here in blue, and it does exactly what the specification is asking for. It leaves occasionally, but it always returns just in time, right? And you sort of see, leaving is measured with respect to the most extreme outer estimation of the set here, and entering is with respect to the more extreme inner estimation here, right? And so that's what you see on this plot. This is just a toy example. Here's a video where we apply this to what I think is a much more interesting system. So this is it's a blimp in our lab. We model it with 12 state dimensions. We're just projecting down to 2 state dimensions here. The specification in this video is kind of similar to the specification on the previous slide. Anytime the blimp enters this blue square in the center of the room, it can do so for, I think, 3 seconds or something like that, but then it needs to leave for 3 seconds, right? And so what it's trying to do is, that's the safety specification. The nominal control objective is just to drive around in a circle as fast as you can, right? But it can't clip the corners too much, because if it clips the corners too much, it would violate the specification. So what we're doing is we have this implemented as what we call a runtime assurance mechanism. It's constantly computing whether or not it can satisfy the safety specification. It's computing reachable sets of the system using mixed monotone systems theory. It's checking satisfaction of my specification using interval signal temporal logic, and it's constantly making sure that it's not going to violate the specification. And if it ever is at risk of violating the specification, it will override that control input, and that we get by solving a mixed integer linear program online. And kind of the other part of this video is I can do that fast enough, these mixed integer programs for signal temporal logic with some kind of clever warm starts and things like that. I can do that fast enough that I can do that in the control loop. So I'm getting verifying safety online. And even if my clock were to time out, even if my mixed integer linear program were to fail, the way we have this whole pipeline structured, the way we have this whole optimal control problem structured, I always have a known safe control input from the previous computation step. So it really is verified safe as it goes along. And as you see, it's doing exactly what we would want it to do. It lets the blimp clip these corners of the safe set, but not too much. And it makes sure that the system is always safe. The red boxes are sort of this reachable sets that it's computing over time as it goes along with this set. Okay, so let me keep moving. Let me just very briefly highlight some other things we're doing with this basic computational framework, these basic computational tools. One of them is trying to go to manifolds. This came out of a real-world experience. We were trying to, again, you saw that spacecraft example from the first couple slides. We've been trying to take some of this theory to quadrotor control. And there, if you're familiar with any of this, even on the blimps, but we were sort of able to get around it a little bit on the blimps, it makes a lot more sense. You have to really model the orientation of these things as manifolds, right? As SO3 and as quaternions or whatever, right? And so, you can try to pretend that these are Euclidean spaces, but these methods tend to get pretty conservative pretty fast when you do that. They're correct. They just tend to be conservative. So what we've really been trying to think about carefully is what is the correct numerical way to do these reachable set computations on these types of manifolds, and particularly groups, motivated by these kinds of applications. And what we've done is we've been leveraging tools from geometric numerical integration. These are tools designed for solving ODEs on Lie groups, and we're using these kind of same insights to solve for reachable sets on Lie groups. This is another slide that sort of goes into a little bit more of the math. And essentially what we're doing is we're doing interval reachability in the Lie algebra, the vector space, the Lie algebra, and then we're projecting this onto the group, and we're being very careful with how we move around these projections, right? So you can't stay in the Lie algebra forever. You have to kind of continually recenter to new base points. And we're doing that in a careful way so that we retain the soundness of the over-approximations without getting too conservative. And so, for example, we use an inclusion function for what's known as this BCH formula, this Baker-Campbell-Hausdorff formula. So if you've ever done any of this kind of work, you'll be familiar with what this formula does and how it comes into play when you're kind of doing these recenterings from the Lie algebra to the Lie group. And what we've done is we've used inclusion functions of this BCH formula and this careful numerical techniques to make sure that we're getting reachable sets that are not too conservative and accurate. And And so, this is a paper that's pretty theoretical, but we've been trying to push this into our application domains as we go along. This is a paper that just appeared a couple months ago at CDC, and I think it's a very interesting research direction. So we're pushing pretty hard on this as well. Okay, this slide. I don't want to go down too much and too deep into this conversation of control contraction metrics, but another tool you can use for reachable set computations is contraction theory. And so some of you may have seen this as control contraction metrics, contraction theory, etc. What this lets you do is it lets you sort of find norms in which your system is, hopefully contracting or at least not expanding too quickly, and then you can go find balls in that normed space and then use those balls to compute reachable sets of the system. That's sort of in a nutshell, what contraction theory gets to bring to this reachable set problem. At first glance, it may seem like our mixed monotone tools are very disconnected from contraction theory, but it turns out there's actually a pretty clean connection to them. If I use mixed monotone systems theory to find these interval rectangle over approximations, these very same decomposition functions we used to do the mixed monotone reachability oftentimes give us exactly the kind of functions we would want when we're computing control contraction metrics. So for example, to compute control contraction metrics, you need to compute Jacobians of the vector field, and then, for example, find some sort of common Lyapunov-like object for these Jacobians. The mixed monotone framework, already we're computing these Jacobians for the purpose of monotone systems theory. And so we can repurpose all of our computations and couple them with these contraction metrics. And basically what we get is we get this sort of local contraction analysis that's valid in the regions in which we've computed these rectangular sets from the mixed monotone system. There's also this very interesting trick that we've recently discussed and published, we've posted on arXiv, where if I bring in some very kind of careful bookkeeping with these inclusion functions, I can actually get better reachable sets than just what local contraction analysis would give us, especially when I'm focusing on, for example, contraction to a known trajectory. That's oftentimes the use case for these contraction metrics, trajectory tracking. And so what we're showing here in this plot, the top plot, let's see, let me try to remember the details here. So this was a 4-state robotic arm. I think the robot arm was trying to put its end effector in a certain location. There was a known controller that was doing that, and the challenge is to compute over approximations of the reachable sets for the system with varying sizes of initial conditions and varying sizes of disturbances, right? And so, the prior state of the art was these top 3 plots proposed in this paper by Cheyenne Mitra, Chichufan, and collaborators. And it's a very nice result about how you would use some contraction theory to solve this problem. What we've shown is that if we couple that with our mixed monotone systems theory and our decomposition function methods, we can dramatically improve, in this case, the reachable set computations you get. And so in this case, you're comparing top and bottom. So for this sort of first case, there's not much difference because the disturbances are pretty small and the initial sets are pretty small. But as you go, we get much better, much more accurate reachable set computation. So especially in this last figure, this is a pretty high, pretty extreme disturbance scenario. And our method just, the prior method just totally explodes because it's trying to over approximate these reachable sets, and it completely explodes. And our mixed monotone inspired techniques here can really keep the reachable sets very tight as the system goes to this particular point 2.1. Good. So I really need to acknowledge my collaborators on this work. So Saber Jafapour was a co-author of many of these papers I mentioned. He's currently a research scientist at CU Boulder. Akash Harapanahali is a PhD student of mine here that's done a lot of this work. And then Luke Baird is another PhD student of mine. He's especially focused a lot on the signal temporal logic work in the blimp hardware experiments, and there's a lot of good work going on there. A number of funding agencies have contributed to this problem. I think it's a very interesting problem space. A number of funding agencies also, are looking at this problem of learning-based control. So I would be remiss, of course, not to thank them. And with that, I'll just kind of conclude with my thoughts here. In this talk, I showed you that our mixed monotone embedding system, it enables efficient reachability. We can do invariant set computations and contraction analysis. The interval analysis, the inclusion analysis, it makes mixed monotonicity not just theoretically very attractive, but computationally relevant as well. And that's really the glue that makes this computational. These techniques are especially well suited for high dimensional settings. So we've shown how they're useful in these neural network controlled settings. And we can also generalize them to manifolds, which I think is very interesting. direction. So if I had to summarize sort of the philosophy of this talk, the philosophy of the research in my group for the past few years, it's bringing these, these control theoretic techniques, but really pushing them to these efficient and useful computational tools that we've been really pushing on. So all of our papers, and especially all of our code, is available on my website. And so feel free to take a look, download our code, try it out. If you have any questions, email me about the code or the papers, and we'd be happy to discuss or collaborate on any of these topics. So with that, I think I'm happy to wrap up, and I'm happy to take any questions that might have appeared in the YouTube feed or elsewhere.
Thank you, Dr. Coogan. Yeah, there are a number of questions. I think we can get to them first.
Okay, sure.
Yeah. The first question is, in general, what's the main difference of the discussed approach and control barrier functions for collision avoidance or in general safety? In your example, do you account for minimizing control effect as well?
Okay, yeah, so it's a great question. So, I was trying to motivate this with obstacle avoidance. What's the connection to barrier functions? Barrier functions are something you can do after you get these reachable sets. So suppose you have these reachable set computations, and now let's suppose that reachable set happens to be colliding with my obstacle. What do I do about that? Well, I could apply a barrier function to this reachable set. And when in fact we have some papers that do that, we call this the implicit barrier function technique. And what it does is it basically puts a barrier function, but it puts it on projected future states of the system. And that's kind of important because kind of generic control barrier function theory really requires you to have quite a bit of knowledge of your system. For example, if you have high relative degree, you have to build these high relative degree control barrier functions. And at least in sort of the standard instantiation, it assumes you essentially have infinite control actuation capability. If you get too close to the boundary, you can immediately apply a very large acceleration, deceleration, whatever to avoid it, right? So, it's well known that CBFs, you really have difficulties when you have systems with relative degree, high relative degree, systems with hard actuation constraints. Of course, there are CBF-based methods for addressing these, and including some from my group. But this would be another approach to the problem, where I'm computing reachable sets of the system and then trying to do something with those reachable sets. So I think that I wouldn't, these methods I don't consider in competition to CBFs. Quite the contrary, I think that they're very complementary to what you might try to do with CBFs in these sort of safe controls. Another answer to that question is, CBFs are great. However, they do change the controller you're applying to the system. And verification is an interesting question in and of itself. If I have a neural network controller, presumably I want to apply that control strategy for some particular reason, and it makes sense to try to verify it as much as you can beforehand, before you do some sort of safety intervention, if that's what you're going to do. So again, I think that complements very well tools and techniques from CBF theory.
Thank you. The next question is, as far as I understand, the MM is monotone. The monotone based reachability approach can be used for verifying the neural network controller. Can it be used for controller designs as well, for example, as a constraint and model predictive control?
Yes. So for example, our training methods, it's essentially being used to compute controllers. So we're training and we're trying to compute neural network controllers based on the monotone systems theory. So in that sense, we're synthesizing controllers. In the signal temporal logic world work, we were also synthesizing controllers. We were computing these reachable sets and then solving, minimal perturbations. So in that sense, it has a connection to sort of the CBF flavor to it. We're computing an optimal control strategy based on those reachable sets that satisfies the temporal logic specification with minimum perturbation. So yeah, so there are very natural ways to sort of blend the reachable set computation theory with the control synthesis problem.
Thank you. The next question is about what if the system is not MM, and how do you compute the reachable sets? I guess they're asking, like, what if you can't do these over-approximations and
right. So yeah, that's right. So sort of the magic of mixed monotone systems theory is I can actually we have theorems that I can take almost any system, assuming it's sufficiently Lipschitz, and put it in this embedding system that is mixed monotone. So in some sense, the question isn't, what if it's not mixed monotone? Every system sort of has this ability to be embedded in the mixed monotone framework. the real question here is, what if that embedding is too conservative? What if it's computing reachable sets, but they're just way too large to do anything useful with? That's sort of that's really the challenge that we've run into, and that's where a lot of these tools that I've been discussing have come into play. These lifting operations, these control contraction metric operations. I didn't talk about it in this talk, but we've talked about looking for different partial orders than the standard partial order. So there's lots of different angles of attack on this conservatism problem. And that's where we've been focusing a lot of our effort, because we need methods both that theoretically reduce the conservatism, but also computationally we can push on. And so, yeah, so anyway, so that's exactly the right question. We've been pushing on that quite a bit. But every time we do this, we get we find ourselves applying it to systems where we weren't able to apply it before because it was too conservative. So I think there's lots of interesting problems here yet to be explored. Yeah.
Thank you. The next question is about, could you please share a bit on how to choose between interconnection-based and interaction-based approaches in real-world application?
Yeah, so that's a kind of a small detail that I didn't get much chance to talk about. In succinctly, the interaction-based methods, it does a better job blending and accounting for the linearizing effects of the neural network controller, but it's just more computationally expensive. It uses a different decomposition function that's a little bit more expensive to compute, because I have to sort of evaluate the Jacobian at more points in the state space, but it tends to be more accurate. So really the trade-off is, are you willing to spend a little bit more computation effort to do the interconnection method is really the question. Yeah.
And I have this question, like, while we formulate a decomposition function for the open loop system and an inclusion function for a neural network controller, and then blend them later, like, what if we don't know the open loop system as such? Like, what if we have to do some exploration before we could even formulate these decomposition functions? How should one deal with that?
Yeah, great question. I mean, so fundamentally, everything I'm proposing has still been model-based. I have a model of the system. I might have some disturbance inputs. I might not know my controller yet, but I'm going to find my controller or use my controller in a model-based setting. That's a totally fair question and critique here, right? I personally am just a very model-based person. I think it's important to use models, and I think it's important to have models. So that's the kind of framework we take on this. We have a different line of work where we kind of get at the question you're asking. Instead of just assuming we have some sort of unknown disturbances W that enter the system, we really try to think carefully about what if that disturbance, is some unknown function. So now I have my dynamics. I have a known component and I have an unknown component, and I can put as much in that unknown component as I want. What we have some work where we've been using Gaussian process theory to over-approximate that unknown component. We can use that Gaussian process theory blends extremely well with our inclusion function techniques. In fact, in the code, we have Gaussian processes, and then we just compute inclusion functions of Gaussian processes. And almost shockingly to us, it just works. And so what this lets us do is it lets us sort of explore the state space. We have papers where we explain how, okay, I can continually sample from the state space. I can use that to improve my estimates. That improvement comes from sort of standard Gaussian process theory. But then once I have that improvement, I can get better reachable sets, and I can do something with that. So that's how we've been approaching this problem of how can I couple the control and reachable set computation problem with the exploration and learning of my environment. And we have a recent automatic paper where we tackled exactly this problem. How can I try to explore while achieving an objective kind of using these reachability tools? So yeah, great question. Yeah.
Okay. Thank you so much. And yeah, I think that's all the questions we have for today. Yeah.
All right. Well, thanks a lot. It was a lot of fun, and the questions were great. So I really enjoyed the talk. Thanks a lot.
Yep. Thank you so much for giving this talk, and hope to see you in the future.
All right. Take care.
Yep. Thank you. Yep. All right, everyone. See you next week. Signing off. This is Nishant. Bye-bye. Thank you, Dr. Coogan.